Good morning. Welcome back to the lecture. Today we are going to talk about different aspects of the PFC. Previously we have seen what would be the mathematical solutions, like we solve for the free energy for the different phases, we construct a phase diagram. And we also talk about the physics aspect, so you can relate the phase field crystal with the density functional theory, and especially for the solid-liquid interface, we show that it captures a realistic physics for the solid-liquid interface. So today I would like to move on to something more practical, right? Because most of you have already got this code working. So I think it's important that to show you a little bit some tricks that we use in the PFC simulations, like how do we usually set up the system dimension if I want to have a single crystal without any strain in the solid. Then of course you have already known that if you want to have a solid liquid coexistence system like this, now you can choose the proper density, so you have a phase separation. But what if I would like my liquid in contact with the crystal with different misorientation, right? So in that case, I will need to rotate my solid and find the proper system dimension for the simulation. So we are going to do that first. And once you know how to set up the proper system size, then there are many examples I'm going to show you, and that's something for you to try if you found some of the examples that's interesting to you. All right, the second thing I'm going to talk about the surface energy measurement. So once you have all this simulation, you want to quantify important physical quantities such as the surface energy. So what's the way you can do that? So in contrast to the phase field model, usually you have a double wave potential. So you know everywhere the energy except the interface should be zero. So in the phase field, just do a simple integration of the energy over the space. Then there you can get what we call the excess energy, and that will be the energy associated with the surface. That is surface energy. But in the phase field crystal, it's kind of tricky because like the calculation you have been doing for the phase diagram, you have seen that the free energy density for the solid liquid, they are not exactly the same, right? We have seen this common tangent construction. So how to exactly calculate the surface energy or excess energy for this solid liquid interface or the grain boundary solid-solid interface, that will be something I'm going to talk about today, all right? And the third thing is also quite useful in studying the mechanical behavior of your phase field crystal solid, is that in a phase field crystal, what we got from the evolution equation is just the density field, right? You have this psi as the function of space, and it's going to oscillate in space. So the local maxima give you an atom, right? And you are waiting for the next local maxima that corresponds to the other atom. But that kind of density description is useful because it's sort of like a density functional theory, so you don't have to track the position of each atom. But in solid mechanics, usually it is quite useful to pinpoint the exact location of each particles. So there you can track the motion and even calculate the strain, things like that. So how can you start with the information of this precise field of space, right? Roughly, you can use a very simple method just to say there seems to be a local maxima occurring at certain coordinates. But if you really want to get the accurate position, especially when you do the strain calculation, you will need a very accurate, accurate number just for the particle position. And how can we do that? So I'm going to show you that you can use the Fourier transform together with the Newton reference method to pinpoint the position of each local maxima, which corresponds to the position of atoms, okay? Okay, so first thing first, I'm going to talk about the way you can set up the system dimension for different crystal orientations. So here, just a very straightforward, the simplest case for solid that you can have in your simulation, right? So you have this triangular lattice, or you can actually see this hexagonal lattice if you look at this one, right? And you have one extra atom here. Then for a periodic boundary condition, so if your system basically you require periodic boundary conditions, there must be a minimum system size you can have for repeated crystal structure. So for example, if I want to just put this orientation kind of hexagonal lattice in my PFC simulation, you can see the minimum size will be this small rectangle, right? Right, because once you go out here, you basically in X direction, you start to repeat yourself. So in the X direction, that will be your minimum system size along the X direction. In the Y direction, basically, that would be the height here, right? So I've shown you previously that the system size now, if you identify the size here, that would be 4 pi over square root of 3, and this side will be 4 pi, okay? It depends on your purpose. If you want to only measure the solid-liquid interface, for example, I just want to measure the solid-liquid interface for this solid orientation, so which means I'm going to replace above atoms with a homogeneous state, just liquid. So you have the bottom is solid and on the top is liquid. In that case, you don't really need to go multiples of cell horizontally. You only need to keep only one very simple unit cell, but in the vertical direction, you are going to expand your system, maybe make your system like 1,000 or 2,000 unit cells. So you really have a very extended dimension. You will roughly set up like half liquid, half solid. And since along the horizontal direction, you are having this periodic structure. So when you really want to just get the interfacial energy for this horizontal solid liquid interface, you don't need a system in the horizontal direction go beyond this length, right? Because it's already started to repeat itself. And on the contrary, if I want to get a solid liquid interfacial energy along this lattice plane, so on the left could be the solid I set up. On the right, that would be the liquid. But in that case, I only need to set my vertical dimension to 4 pi, is this distance, right? Because anything above that is going to repeat itself. So it depends on your purpose. You can set up how many unit cell, like n by n unit cell you're going to have. So for this case, it's quite straightforward because you can simply set up in horizontal direction, that will be a multiple of this 4 pi over square root of 3. And in the y direction, it will be the multiples of 4 pi. And then you can always fit in several triangle lattices. All right, but of course, if we want to, for example, to get the solid liquid interfacial energy for different crystal plane, for example, let's do cut from this atom to this atom, right? Because you can always make an arbitrary crystal plane, right? So if I have something cut through these two atoms, then I will need to set up a system that actually half the system is solid, half the system is liquid. But the problem now is, in that case, what should be the new length, new dimension in the x and y direction respectively, so that I can fit this rotated crystal into my simulation domain. So just to give you a solid example, so here is a solid rotated by theta, right? So which means I just rotate the lattice on the left by an angle theta. So now the question is, if I'm doing this, right, but my simulation domain is still in rectangle, right? So still have something is, I need to figure out along the x direction, what should be the new system size and what will be the new dimension in the y direction. So I'm going to draw certain rectangle. But once I draw that, actually I will see, I will have a periodic boundary condition. So whatever goes out to my simulation box will be periodic going back here, right? So clearly that the system size for this crystal is not arbitrary. There is some geometric relations that you can choose from. So let's talk about that. All right. So in order to do the calculation, let us define useful factors, right? So let's go back to the left. So since the lattices are repeated structure, so I can define two useful lattices, two useful factors for hexagonal lattice, right? So I can define one factor like this red factor, all right? So that will bring me from one local atom to the other local atom. If I only have the red vector, I can only go horizontally. But with the other vector, the black one, right now I can go from the one on the bottom left to this atom. And for any other atoms, I can always use the multiples of A vector, this A vector, plus the multiple of the B vector to get to the other position of atoms. All right? So, in a sense, I can use this A vector and B vector to figure out my dimensions. Why? Because now the question is, if I just go from atom to atoms, right? If I go along in the B direction, the question is, how many B I am going to take? So in the horizontal direction, the length is just equal to this red vector, because after that, I'm going to repeat myself. So there's always a relation between the summation of how many A plus B that will brings you to the periodic structure. So even for a lattice that's being rotated by angle theta, you can also use that relation to determine the system, the size of box you should have to put the stress-free solid. Okay, so the following is just the detail, but the concept is there. So since those two vectors are very important, that can bring us from the one location of atoms to the other. So first thing, let's figure out, in those two vectors are being rotated by angle theta. So if I write in terms of xy coordinate, so x here is always the horizontal direction, y is the vertical direction. So you can see this A vector initially only have x component, but now because I rotated by theta, so it has projection in the x and y direction. And that will be the cosine theta and sine theta respectively. Okay? So what we just did is just to apply a rotational matrix to the old vector, to the vector on the left. And the rotational matrix, would be something like a cosine, minus sine, and sine structure. Okay? So you can do the same thing for the black vector, right? So that's something for you to check out, but I just list the answer here. Just plugging this B to the right-hand side of this equation, then you are going to get the B vector being rotated by angle theta. And now you've got the xy component still in the x, still project to the, you will get a new xy component like this. Okay, so that's our foundation, and we are going to use this kind of picture to construct what's the system size. All right. I think it's straightforward. Okay, we need more space, and let me move those two important factors to left. All right, okay. So the blue dashed line is a reference so that we know where is the y direction, and horizontal direction you can also draw that. That's not important. So the question again is that how many if I go along the black direction, so corresponding, which means I can go from here to the atom next here. If I just adding the other black vector, I'm going from this atom to the next atom here, right? So the question is always about how many repeated steps you have to take so that when you reach that direction, you can add or subtract certain units of the red vector, so that will bring you back to y equal to, bring you back to x equal to 0. Because we are starting with x equal to 0, right? So if I go along this way, if I can go back here, so that means what? That means, so that means the system will start to repeat itself vertically after the projected Ly length. Is that right? Because quickly, the order is right. The order is wrong. No, that is right. So the mathematical condition basic is that using a multiple of B to go to certain atom, then I would take, in this case, that would be one A vector, so I subtract this unit. And once I have done that, I'm ending up with x coordinate equal to 0, right? And whatever the corresponding y-axis is going to be my system dimension. But if I guarantee that x equal to 0, which means I will find one atom here. So initially I have an atom here, and that will be the other atom here. So it's going to be my periodic structure occurring along this direction, right? Make sense? Okay. So similarly, let's do the other side. So I can just fix just one, for example. This is for, here you can, in the original example, you can even go, because you probably won't find always there is just a few multiples of b, and adding up with our subject 1a will bring you back to x, right? That's probably not most of the case. You probably have to go few times of b and also few times of a. So here, just for example, you just for simplicity, you can just draw easier here. But something similar is that you can also go in different direction. Now I can go multiples of a, right? But clear here is that if I just go 2, if I just subtract this black factor, it's not going to bring me back to the horizontal axis. So in this case, you have to keep going and going and going to a certain height, and you can check whether if now you are subtracting 1b, that will bring you back to this horizontal line, which means y equal to 0. You are starting with y equal to 0, and you are going through different atoms, and a new atom can appear here, right? So in the x direction now, the system could be also periodic. Right, and just the direct translation from what we explained graphically, that would be how many times that n times of a factor minus how many times of b factor, that will bring you back to the horizontal axis, which means y equal to 0, right? And whatever we are getting out of this length, that will be my simulation dimension in the x direction. Okay? All right. So let's work out, here's just a concept, let's work out some algebra, right? So for example, let's look at the first, so we have 4 equations. So the x component summing here has to be equal to Lx, and the y component of those two sum has to be 0. The same thing, there are 2 more relations out of this A and B combination. So let's look one of these four relations first. So the first 0, which means n times a. So I just simply plug in this a vector, right, in the rotated frame. So I have n times, because I only care about the y component. So this n, I only have to multiply by this sine theta, right? So it's n sine theta. And now it's minus b, minus m times b. So minus m is here, and b I only also take the y component, right? Because everything I evaluate just for the y component. So you can see I just copy everything here and throw in here. So now I have all this just simple sine cosine function and also 2 integers, right? So I can move around and get a relation saying that from this 0, one of the relation, I can have a tangent is a function of those 2 integers, okay? So now you can pick 2 integers and see what the tangent data. But the problem is that that's also, once you pick those numbers, what you are getting is that you are going to see a repeated structure in the x direction, right? Because we are starting here. But there is no guarantee in the y direction it's going to be periodic. So I can do the same thing just by looking at the other 0 here, right? So I'm going to leave you with the result. So you can similarly get this from this constraint, the tangent theta has to be equal to j over j minus 2i divided by square root of 3j. Okay, so you have to check whether you can have a pair of m and n and a pair of I and j, they all give you the same angle, same tangent. If yes, then you can pick those ij, mn. Okay, and once you know that, what is your Lx? Because you have know what's m and n, just plug in whatever here for the x component here. then you figure out what's your x dimension. And doing the same thing for this Ly, once you know I and j, then you can know the y dimension. So now you can probably set the simulation for that. Okay? The m and n here will be how many ray factor I'm going along here and substitute that. Yeah. Right. In the those the A and B are A is this factor and B is this. Right. Ij would be how many times you are going along this direction, right? Yes. And B is how many times you're going in that direction. So I and j are also two integers. So the only constraint is I, j, m, n has to be integers. And the other constraint is that you have to find the possible pairs, right? Not all the integers can just plug in and satisfy the equation on both ends, left-hand side, right-hand side. So let me give you one example, or many examples actually. So you can check all those numbers I'm listing here will satisfy this tangent relation, okay? And so, which means I can rotate, I can start with this triangle lattice, right? And rotate by any degree. Like first example would be like 10 degrees. Let me just jump there and move this to 10 degrees, right? Then I always, my habit's always to keep m equal to 1. So that's somehow, which means, and what the picture in my mind is that I always seeking a relative smaller n here. So the smaller n is, which means you just go few steps, you will go back. So that corresponds to a larger misorientation. But if you really have to go many times of A, then subtract 1B, then that corresponds to a really small misorientation, right? And as you can imagine, if those numbers are larger, when you do the calculation for Lx and Ly, it's going to be insanely large. So there is a price to pay. I mean, in PFC, you got all the atomic detail, right? But in order to really fit in a periodic calculation for those details, for the small misorientations, you have to really set a proper boundary in order to have a stress-free solid. All right, so here is just one example, just to complete the first part of this lecture, is that we can actually calculate Lx and Ly. And in this case, m and n is 1 and 5. So the x component will be like 5a in the x component minus n is 1. So minus b, but we're just taking the x component of it. So you can see it's 5 times the x component in A, that's cosine. And we know the angle is 10.89. And minus 1 times what? The x component from B. So I'm plugging everything here, right? So it's 2 cosine over 2, and also minus square root 3 over 2. So I have to pull out the 1/2 here. So everything just a number. So you know now if you set your Lx equal to 33 something, and do the same thing for Ly, that'd be 36. So once you do that, you get this. So you can see the aspect ratio looks right? Here it's like 33. That's the y direction is slightly longer. Is 36. But now that's the way you can fit in. That's the minimum size you can have for this 10 degree or roughly 11 degree rotated lattice. Now, if I just make multiples of this system and connect them, maybe say in the x direction, right? Then I can cut my system and to study the solid and also the liquid interface. If I do that in the y direction, I can get it solid and different, or in the liquid interface on the other side, right? Okay, so let me see if I have, yeah, I already timed. And you have to use this 4 pi over square root of 3 because in your evolution equation, you always have already set this Laplacian plus 1 kernel. So that 1 is already there. So because of that 1, for triangular lattice, you have to really use this A is 4 pi over square root of 3. Yeah, so I have to use A equals to 4 pi over square root of 3 in my calculation. Okay, but that's not the, still I have a few things to say before we can close this part. is that we know the system dimension, right? So that's what you can say, what's my Lx, my Ly, but you still need the n size to really have a periodic structure appearing in your simulation. So we know for a triangle lattice that in PFC will be some mean density plus this 2A and all six plane waves coming together. But you can see here, I put down this x prime, y prime, and y prime. It's in the primed coordinate system. So if the grain does not rotate, or what I should say is that if you just plot this and doesn't distinguish what's the prime coordinate and the unprime coordinate, what you are getting is just unrotated lattices, right? So there must be a trick that I can get starting from here and to get this rotated lattice. And that's also associated with rotational operation. If you simply replace the x is, so there's a relation between the rotated reference frame and the unrotated one, because they are associated with this rotational matrix. You can relate that the prime coordinates is simply the rotation matrix times the original x and y. So this x and y is the coordinate for your rectangular system. So you can have dx, dy, dx, 2 times dx, etc., right? So for any place, you have to calculate this prime coordinate first and plug in here. Then for example like 10.89 degrees, just select those numbers and plug in. And once you set this dimension and saying your psi has to look like this, and this graph is something you are going to get. Okay? All right, so I think that completes how you can set up proper system dimension for stress-free solid. Any questions? Okay, yeah. Yeah, so in 3D, what I would suggest is that, for example, let's say BCC, then let's say my first, I always fix, for example, like z-axis. So if I just say setting this plane interface that's along the normal, for example, like still 100, now I can just start, I can always rotate around a z-axis. So it's always like two-dimensional problem, right? So I'm just rotating like a square lattice to rotate by a certain angle. So in that operation, you can still have like four numbers because there's only one angle. Yeah, you can, for 3D, you probably have to first to choose a structure that's easier for you to do the rotation. Yeah. So once you fix that axis, everything becomes a 2D problem, right? So let me give you a challenge or a quiz. The problem now is to find the pairs of like I, J, M, N, right? So now you can know what's the rotation and what will be the system size. So can you find what will be the smallest system you can have for this hexagonal lattice? But that angle cannot be 0 and 30 degrees because 0 and 30 will be quite trivial. 4 pi and 4 pi divided by square root of 3. But I'm showing you here like 10 or 11 degrees, quite small already. But just give it a try to see whether you can have a different pair of M, N, I, J that corresponding to a different orientation, but whether your system would have, let's say, smaller area than mine. So my system area would be like roughly 33 square, right? So can you find something smaller than my system? So maybe let's take 10-15 minutes. You can work out like all this detail and trying to find your own IJMM pair and to really work out the misorientation system size. Okay? And just feel free to let me know. Yeah, so that's the goal. Yeah, 30 is kind of cheating, right? It's still 4 pi. Yeah. Okay. So good to see here. No. So when we do the grain boundary energy, and we just create the system size for the stress-free solid. So for example, we have been talking about the solid-liquid interfaces. So now you can actually have a system that have a different crystal orientations. This is not either 0 and 30 degree. Actually, it's a solid rotated by a certain degree, right? But now if you run a simulation and wait long enough until the system reaches equilibrium, then you can measure what's the surface energy. Right? So that's one of the applications. You can also set up like grain boundary, because now you know how to fit in with certain crystal of some misorientation in one box, right? So now you just prepared exactly the same 2 boxes, but for one side of the box, just to stuck in with the lattice rotated by positive theta degree, the other will be negative theta. Because you will see for positive and negative theta, you are expecting the same Lx and Ly. But now just putting those 2 boxes together, now you can have a grain boundary. It's a symmetric tailed grain boundary, right? On 2 sides, you have a positive and negative theta. So in this case, it's plus minus 5 degree, okay? But actually, you can do something else. You can also have some other, yes? Yeah, so I didn't show the other side. I didn't show the far side. So it's going to be pure. So the system is going to be really extended here, and the periodic boundary. So there will be the other grain boundary here and here. That's right. I only show one side. All right. So that's a good question. But I can also have this, I would say, the same misorientation plus minus 5 symmetric tilt. But how can the grain boundary structure become immediately different than what I have on the left-hand side? So the green arrows I'm drawing here is the Burgers factor for the local dislocation. So you see the fundamental difference is that if I zoom in locally, what's the crystal structure? Basically, those 2 things, they are differ by the reference frame. For example, if I initially have this kind of reference lattice, and then I just cut my crystal in half and rotated the left and right angle by 5 degrees and put them together, that would be something I will get in here. So you can see roughly the atomic structure I'm showing here, I basically is locally zoomed, is quite similar to this one, right? It's just rotated by positive and negative 5 degrees. And you put together, you can have a Burgers factor roughly aligned parallel to the x direction, because the Burgers factor has to be in one of the lattice plane. So this factor corresponding to this direction, okay? So what happened to the different grain boundary structure we are showing on the left-hand side? That is actually, if now I just rotate the system by 90 degrees, or I keep the same lattices, but now I'm just cutting the crystal half this way. And for the upper lattice, I rotated by 5 degrees. For the lower lattice, I rotated by negative 5 degrees. And once I have that, the grain boundary structure along the surface will be something like this, right? So once I do that, I can just rotate everything by 90 degrees, and that will give me something that look like this. But since we know for triangle lattice, the Burgers factor, they can all, just like I described, is the direction connecting all the atoms. So by simply rotating 90 degrees, the allowed Burgers factor are different. So although I always trying to have, although I always showing this symmetric tailed boundary with the misorientation positive negative 5 degrees, but as you can see, the atomistic nature of the lattices, the discrete nature, immediately gives us something quite different. Although we are talking about the same symmetric tail with the symmetric tail boundary with the same misorientation, but the structure itself is already different, and that's very realistic, right? Okay, so with the knowledge before how to set up a stress-free PFC simulation, you can already carry out the grain boundary calculation. And because you also know how to set up misorientation, you can also start with a single crystal and just say for certain area of your triangle lattices, you cut a circle and rotate the center grain by, in this case, 20 degrees, and let the grain relax. So you are starting the grain growth problem. So here you are seeing a very nice curvature-driven motion come in. And you can also try to have the system with smaller mesoneration, like 5 degrees. So you are expecting the grain boundary structure will be something discrete, and the dynamics will be quite different. So that's something also we can already done that with the system size property set like we just discussed. And some more advanced example that might interest you is the grain boundary grooving that require the knowledge of setting up the bicrystal. So it's a knowledge for how to set up the stress-free bicrystal like we showed before. And now you also know how to set up the proper density so the solid can coexist with the liquid. So with those two knowledge combined, you can study something like the grain boundary grooving. And also for this solid liquid system, here we don't have any bicrystal. So you just need to figure out a system size for a single crystal. But now you just pick up the mean density that will give you a solid liquid coexistence. But the example I'm showing here is not just an equilibrium solid liquid interface. It is actually a solid being stressed. So one way to implement the stress, which means you are going to bring your stress-free solid and try to apply a strain on it. One of the simple way to do it is actually first set up the proper Lx, Ly in your system, so everything is stress-free. Then you can also assign a proper density profile as your initial condition. But when you actually start to run the simulation, you are saying that Lx is not the proper Lx you are giving in the very beginning. It is just like 99% of the value you are assigning. So if let's say Lx is 100, but now I'm just saying when I run a simulation, the Lx is actually 99. So which means the nearby atom will feel the size being squeezed by 1%, right? And that kind of squeeze is going to increase the elastic energy of the system, right? So the energy is being increased. But we know the free energy or the thermodynamically, the system is going toward the energy minima if possible. So the way the system is going to relax all the elastic energy being stored in the solid is by undulate the surface, right? Because you can think about if you have something is being a mountain, because I'm compressing something, but if the solid can somehow being bulge a little bit. So what happens is that for the bulge part, you have atom coming out, but there's no atom in their neighborhood. So which means locally, those solid can expand their lattice spacing a little bit. By that expansion, they can release the elastic energy locally. But locally, if you have this lattice plane being relaxed doing that way, so that kind of relaxation is going to press the nearby atoms, especially for atoms already in the trough. It's going to be more compressed. So which means the elastic energy for those parts is going to be increased, but overall it's going to release a little bit more the elastic energy. So that's why you are expecting once there is a slight, very small number of perturbation, this kind of instability is going to happen. So that's something you can already do with all the knowledge I just showed you, okay? In the right direction, yeah, there will be the other solid liquid surface. Yeah. So at the bottom, there will be the other liquid, right? So actually, you are observing something similar happen on the other side. And especially when you see this defect coming out, that defect is attracted by a defect nuclei here. So they are all coming to each other and get annihilated. Yeah. All right. Okay, second topic today is about the solid liquid surface energy measurement. Because we want to get physical quantity that we care about, and we want to measure that quantitatively. So, as I just discussed a little bit before, if you just want to get the solid liquid interfacial energy, you don't really need a very extended dimension along the y direction. There's no need, because once you found out what's the minimum periodic boundary condition in the y direction, everything you just do extra along the y direction is going to, they all contribute the same. So there's no need to go in one periodic structure. So Ly is always, you have to set as a minimum length for the stress-free solid. But on the contrary, you don't have to worry about the periodicity in the x direction, because it's a solid-liquid interface. So the solid is not coming back to the other end. So the geometric constraint for this kind of system is less. So usually you can really try out several different means orientations, because the only thing you care is probably to select your simulation with several Ly. They are not large, but you don't really have the other constraint in the x dimension, right? So that's the system setup you could have for the solid-liquid interfacial property, all right? Then, like I just say here, and there is no really a constraint in the x direction, but usually you want to avoid something. For example, you should at least observe what's your interface width, right? It's a solid-liquid transition. Like the example I'm showing you here is a 2D hexagonal calculation for epsilon equal to 0.1. So the interface width is roughly, I would say, 5 to 7 atomic layers, all right? And so if I want to have a system for solid-liquid coexistence, I will try to have the dimension at least be much larger than the interface width. Because, for example, if I have a periodic boundary condition, I'm expecting 2 solid-liquid interface, right? Because it's periodic. So I would like to avoid a solid-liquid interface interaction. So I want to keep those two interfaces far enough. And also I want to have a really nice representation of the liquid phase and solid phase. So one constraint only is actually trying to make your system as extended as possible, relatively speaking, to the interface width, all right? So that's the simulation you should, simulation setup you should pay attention to. But the way to measure the surface energy is quite straightforward, because the definition of the surface energy is the excess energy of the system compared to the one without the interface, right? So the equation we're writing here is actually doing that, because the system without the interface is what? If you have set up your PF system, the PFC system with the mean density per side bar, right? So we know there's going to be a phase separation, and the phase separation is going to follow the level rule, right? So if you are really close to a solid density, you're going to have a more fraction of solid, and if you're really close to a liquid density, you're going to get more liquid. But that's a thermodynamic calculation, and there's no interface involved when we talk about the level rule. So if I start with a simulation of per side bar, the solid-liquid fraction is going to follow a very simple level rule, right? And the energy without interface is just a linear interpolation of the solid fraction times the solid density and the liquid fraction times the liquid density. That's it, right? So the red box one is the one without the interface. And the F in the integral here over space is basically the free energy of the total system. So the first part basically is just to plug in whatever the per side field is back to the phase field free energy functional, and that's the total energy of the system. So here simply we just calculate this contribution and minus the free energy of the system without an interface. So that's the idea, right? So that's very straightforward. The total energy that you can calculate with this per side field, and the rest of that part is the one without interface. And this thing you don't have to do, you don't have to carry out the integral, because although I'm writing in this form, you can see that you have a solid liquid coexistent density, and also the solid free energy density and the liquid. There's a typo, and there should be a solid and liquid. So here basically is the, according to the level rule, what the energy is. But as you can see, if you carry out that special integral, right, what is the integral of psi over space? Because all others, they are just numbers. So here, basically, what you are having here is just the mean density, right? So although I'm writing in this way, actually it doesn't depend on the detail of psi, how it distributes in space. Once you know the mean density, you know this term, what's the reference energy you should be subtracted off. Okay, so this method seems straightforward, but to actually have an accurate determination of the surface energy, of course, you know pretty much about this psi bar. That's something you give and will not change over time. So you know exactly what number is. And this f, you can do this integration in the Fourier space, like what you have been doing for your evolution equation. If you evaluate the derivative in the Fourier space, it's going to be very accurate. So f can be calculated easily. So the first part is not a problem. And the second part, we need to know 4 things. What is the coexistent density? And this, if we want to get a really accurate calculation, we should not use the one we got from this one mode approximation, because in the PFC simulations, actually you are expecting more mode than one mode in your density profile. So actually you should get all those coexistent density and the free energy density numerically, right? So which means it's a full simulation results. So you will need to accurately to determine what is those numerically the coexistent density and their corresponding free energy density. Once you know that, and this calculation is trivial. So is that hard to get, or why is that a problem? First, you have the solid liquid coexist with each other for the liquid side, right? So you have already seen the system reach equilibrium, and one side is liquid and one side is solid. And for the liquid side, it's really trivial. You only have a constant over that part. So just read your data, you will know what is that constant. So you will have a very nice, a very accurate number for the liquid coexistent density and also its corresponding free energy. So there is no problem to get this psi bar liquid and F liquid, right? But what's tricky is, we know on the solid side, it's actually everything is oscillating. So the mean density, the density field is, and also the free energy is, okay? So we want to get the mean density. F should be the also the average one, the average density over one unit cell. But usually, for one unit cell, especially you have solid liquid interface, sometimes the atom will not really sit on your mesh point. So doing that numerical integration could be a problem over one unit cell. So what's a better way to actually get this, for example, what's the solid density and the free energy density? The way is that to really accurately pinpoint that thing, we can use the information we have obtained in the liquid side. Since the system is going to reach equilibrium in the end, the chemical potential everywhere, in the solid, in the liquid, even on the interface, they are all the same. They are all a number. And that number we have already known, because we know what's the coexistent liquid density, right? That's something we just read from our simulation. And there is a very simple relation for the chemical potential, right? Which is a functional derivative of that. And for the liquid, it's quite trivial. It's just a linear term and a cubic term. It's a function of psi bar only. So you will know what's the coexistent density numerically to a very accurate degree. So that's something on the solid side has to match. At the equilibrium, the solid has to reproduce the same value of the chemical potential, all right? So how can we get that information? So which means, do we know at what mean density of solid, the solid will have the chemical potential equal to mu L? And now we don't really care about what happened in my solid liquid coexistence. I only care about, for one unit cell of the solid, what's the corresponding mean density when I run the simulation and wait this one unit cell of solid reach equilibrium. What's its chemical potential? If the potential is what I desire for, like mu L, then I know that's the coexistent solid that I should be getting. I should be using in this calculation. So the idea is following. Once I know what's the equilibrium chemical potential from the liquid side, right? So I have some goal to match for the solid. Now I just start with a very simple 1 unit cell calculation, and usually you will reach equilibrium in almost no time. And what I can try is to start my simulation with different mean density, and once I have that value, I run the simulation and wait until it reaches equilibrium, and I can calculate I can read what's the chemical potential of the solid. And note that although we know the density field and the free energy is a function of space, but the chemical potential is not. The chemical potential will be always the same everywhere. So once I have something at the equilibrium, if I just try something, because I don't really know what's the coexistent solid density, I will try something freely. So once I have something at the equilibrium, I will get a point and to report what's the corresponding chemical potential for that setup. So if that's too high, I can adjust my mean density. If that's too low, I can adjust again. So I can get to a point that's really close to the right chemical potential. Then usually if that's really close to, if I have several points and that's really close to each other, it's going to be a straight line because everything can be done through a Taylor expansion, and if the difference is small, it's going to be a straight line. So we can easily do an interpolation to get what is the expected coexistent density for my solid. And that's information we are going to use for this calculation, okay? And since I have already carried out that calculation, I can also do that for the free energy. So the free energy there's no problem because that's 1 unit cell, and the mean density is whatever I have integrated over the space and divided by the volume. So from there, I can have all those 4 unknown determined, and plug in this relation. I can have the surface energy measured. Okay, that's the first way to do it. Aside from the typo, everything is correct. Any question? Okay, so that's let me see. That's something repetitive. Sorry. Okay, so let's go to the second method. You can also do a different way. That's quite common. People are referring to the 2008 paper also to carry out the solid liquid interfacial energy calculation or the grain boundary energy calculation. Okay, so let me briefly discuss the method they present in the paper. Is that you have a solid, liquid, and the interface, right? If you are using a periodic boundary condition, you might have an extra interface here. So, but here just for illustration, I just show you a system with only one interface. Okay. So, in the PFC model, there is an interface width L gamma, and also for a system size with the dimension Lx times the cross section, you are expecting the solid fraction and the liquid fraction, when they add up, they will not be exact to 1 because they will also be a fraction for the interface. So you are expecting, if I only look along the x direction, the system length of solid plus liquid plus the interface will be exact into my system dimension, right? So that should have 3 contributions because the interface here is not 0. There will be something. So what will be the total energy of this solid liquid plus this interface? That will be the solid density times the solid volume, and also a contribution, the same thing for the liquid, and also a term from the interfacial energy, right? But for interfacial energy, usually it's measured in the energy per unit area. So here I only multiply by the cross-sectional area, okay? So that's quite general, but if we talk about a special case in 2D, then the A here just simply, that's my Ly, and the volume is just the Lx times Ly. But in quite general, you can write that as in 3D case. So now if I divide everything by the total volume, I can get the free energy density of overall the system. So that's something when you carry out the PFC simulation, you can have this number. So just integrate the energy over the whole system, then you can get the number on the left-hand side immediately. So what happened on the other terms on the right-hand side? So when you divide by the total volume, so this term basically will give you the volume of the solid divided by total volume. That will give you the volume fraction of solid, right? And the volume fraction of solid will be also equal to the length ratio. And the second term will be the same thing for the liquid. And the third one, because I divide by the volume, so I have this 1 over Lx factor here, okay? So now the trick is, if I can have a really extended system in the x dimension, so I'm requiring that Lx is much bigger than the interfacial width, then if I divide this relation by Lx, the last term can drop out, right? If that's the limit. So roughly, I can ignore the interfacial width if my system is really extended. So if that limit holds, you will see the first term basically will be always the same constant for your system. If and only if you run the simulation every time with a fixed value of per psi bar. So you are expecting the phase separation, the fraction of solid liquid has to follow the same level rule. You can try your system size differently, right? For example, if I'm trying in the first time Lx and for value of a per psi bar, I have a phase separation. But now if I just try twice the system size, but with the same value of per psi bar, I will expect to have the same volume fraction for solid and liquid. So this F0 is just a linear combination of the free energy contribution, so it's always going to be the same number. So the energy underlying here, we call it F0. That is basically always a constant. If we run the simulation always with the same mean density, like for 2D hexagonal, if we set epsilon equal to 0.1, per psi bar is always like minus 0.198. If we always fix that, but we can try different sizes. The first term always is a constant, right? But that gives us a very nice relation, which is this. So what I'm going to do now is I'm going to run the same simulation, not the same, a similar simulation, but with different size. But since whatever on the right-hand side, the first term on the right-hand side is always a constant. If I run the simulation only with a fixed per psi bar, but different size. So F0 is always a constant, but F is going to change different. And every time I will using different system size, I will get a different energy. But now if I only make a plot with this energy density versus 1 over L, from the graph I can measure the slope, and that slope is going to be the interfacial energy. All right? So basically, you start with one simulation, you're getting what's the 1 over L, and then what is corresponding free energy density. It's better to increase the system size so that the interfacial width is always negligible, right? So you can have same thing repeated and have more and more data. Then you do a linear fitting, and from the graph, the slope will be the surface energy of your system. So you can try it out. And what you are going to find maybe is that if your system size is not large enough, right? If Lx is not that large, so 1 over L on this graph will be somewhere here. If Lx is not large, so you will have several points here. So you can populate your data along the, for different value of Lx. So you have several data. So sometimes you will see the point on the right could be off, and only some data on the left-hand side will agree with this linear relation. The reason is that probably is because if the system size is not really much larger than the interface width, the approximation we are making here is not that good, right? So it's better just to extend your system in the x direction as much as possible. So in that case, you can have a really nice linear relation. You can read the slope, read the surface energy from the graph. Okay? All right, so that's the second part of this lecture. That's the way you can get a solid liquid surface energy. But in the meantime, you can think about something related, is that if now I don't have a solid liquid, I have a solid and solid in contact, maybe a symmetric tilt, right? In that case, can you use something similar to evaluate the grain boundary energy? If you can, then what you can do next is just by changing different mixed orientations. So for different mixed orientation, you are expecting that dislocation structure on the surface is going to change, right? So that would give rise to a different grain boundary energy contribution. Then you can make a plot that is gamma GB versus the mixed orientation. And for the really low angle, you are expect to rediscover this Ricci-Shockley relation, right? So, but in order to have all those information, you will need to know how to determine even the grain boundary energy from simulation. So think about this logic and see whether that applies also to the grain boundary case. Okay? All right. So maybe we should continue the third part. That's going to be short, or you want to take a break? Okay. So let's do that. Good? All right, so just feel free to let me know if you have any questions. I will just leave these slides here. Okay. So just for the record, I fixed this negative sign. So hopefully everything checks out. Let me do that quickly. We know that should be there. Yeah, I think now it's correct. All right. So my suggestion to you is that maybe one thing that's simple you can try is actually to get this configuration. So which means you can try to set x and ly by those two numbers, and really just substitute what's your density insights, right? So here exactly for a set of the coordinates, what would be the transform coordinate x prime y prime, and plugging here you will know as you go along in different places what would be the corresponding density field. So to see whether you can reproduce this kind of configuration, right? So if everything works out, you have some confidence, then you can try to work on the example I just showed you, right? So that's the first thing. And the second thing I would like to make correction is that actually here should be F liquid, but the concepts actually we are subtracting the system without a solid liquid interface. So that's actually the energy you can estimate from the level rule. So aside from the previous typo, I correct that this is F liquid, all right? So we are going to talk about one more thing, is to pinpoint accurately the atomic position of your, in the phase field crystal, basically. So here just one example from one of our paper. So we try to study the grain boundary structure as this kind of bicrystal get compressed. All right. So on the top of the figure is the density field you simulate, right? That's from the phase field crystal. So here you have a psi as a function of space. You have this local peak and something drop, and the density peak will kind of drop down a little bit because during the on these grain boundary structures, because the structure they are so disordered, so you are expecting less atoms can be found around here. But sometimes to really get the location of these density peaks, which means the position of atoms, could be useful because during this kind of deformation, one might be interested in this plasticity formation, or to try to track how the atom moves subject to stress, right? So, or you want to evaluate the local strain. So for all that, you will need to know how to determine accurately the position of each atom. So from this density field, how can you get from this psi to have this discrete information saying that there's one atom sits at x1, y1, and there's the other atom at a different location, etc. Right? So that's basically what I'm going to show you how to do. There are several ways, but I think maybe the Newton reference method is the simplest way to, especially you have been working on the evolution equation, mainly use the spectral method. So it's going to give you a very accurate result using the spectral method together with the Newton reference method. Okay, so our goal here is to get from the density field to the position of atoms. So how to proceed? So straightforwardly, we know that the local maxima or extreme values satisfy that the local variation of the density field must be 0 because it's an extreme value, right? So, or you can write down that as the partial derivative of psi with respect to x and y. If for those places is a local maxima or minima, it's going to be 0. But of course, we don't care about the local minima. We only care about local maxima. All right. So in the following, I'm going to use only 2 things. One is FFT that you are familiar with. The other is just the Newton reference method. That's something we have been used in constructing the phase diagram. You mean what? There we use a symbolic calculation to get the final energy. But how you get those coexistent density, the details actually also using a Newton reference method. Okay. It's quite straightforward, but let me see why Lisa disappeared for no reason. Okay, that is correct. Okay, so what we are having is actually a density field as a function of space. And you know how to do the Fourier transform. So by doing a Fourier transform, you immediately get a set of psi k, the Fourier amplitude, right? So now you have the same degree of freedom either in the real space or in a reciprocal space. But the point is that for a given time, everything is stationary. So when you do the Fourier transform, all those Fourier coefficients, they will not change. They're just numbers or complex numbers, okay? So those are unknown, just numbers from your Fourier transform. So we don't have to worry about those numbers just by doing a Fourier transform. They are known. Okay. So let us define 2 functions. That's called G1, G2. That's the derivative of psi respect to x and y. Right? Of course, we are looking for those 2 functions to be 0 at the same time. And which coordinates will satisfy that condition? That would be the atom. That would be the minima or would be the extreme value of the density field. And this G1, G2 can be evaluated straightforwardly in the Fourier space, right? For example, if I taking the derivative of psi with respect to x, that would just bring down this kx in front of the Fourier coefficient. So I just think it's probably better just switch the summation index from I to j because there's always this ik. So I'm trying to avoid the confusion, although I think I've caused too much confusion before. So when I take derivative with respect to x, immediately you get this the x component of kj. So that's why you have this kjx coming out, right? And also an imaginary number I in front. So as I mentioned, psi k are just numbers. And those kx, ky are also determined by your system size. So they are all numbers. So what it means is that now G1 is just a function of space. So just give me 1 coordinates, x and y, then plug in, I got a value, right? So if for a set of x, y, when I plug it in, that's equal to 0, and that basically satisfies the first constraint. The same thing I can do for the second one, right? So the task I'm having now basically is saying I have 2 functions, G1 and G2. They are function of x and y. And I'm trying to look for a solution of pair of x, y that will make those 2 g's equal to 0. And although the x and y will appear on this density wave, there's a lot of exponential ik.r, and you have to summation, for example, in 2D, 6 plane waves. But you can just throw in a number and ask the computer to do the calculation, right? So that's not that difficult. Okay, so how to find the solution that G1 and G2 that we require it to be equal, which means a local extreme value. And the Newton reference method basically requires that you have to make a good initial guess where is the possible location of the atom. And that is not hard to do because from the phase field crystal simulation outcome, you can just eyeball saying, okay, somewhere around there is an atom. You don't have to be really accurate about it. You can use a very rough scheme saying, on your square lattice, if center grid point, the density of that is bigger than their neighbor, then there's roughly density maxima there. So you can use that to sort of eyeballing and get a very rough estimate, right? Because for the Newton-Raphson method, you will need a good initial guess. So you can roughly just saying, okay, if my guess is that there is local maxima around x naught and y naught, okay? And the scheme of the Newton-Raphson method is the following. So let's say the real solution, the accurate position of atom is at x star and y star, right? So what we mean by x star and y star are the accurate position, which means those two g function, if I plug in x star and y star, has to be 0. But now I only have information, or my guess is roughly there is a maxima around x0 and y0. So that is do the Taylor expansion of the g1 function and g2 function later with respect to the x0 and y0, okay? So if we do this Taylor expansion, we got the first term is just a value of g1 evaluate x0, y0. And other two terms evolve. G1 take again the derivative with respect to x and y and times the difference between the x star and x0, those two things, right? And they are higher order terms. But if x0 and y0, they are really close to the x star and y star, then all those things are really, really small. Right? So it depends on how good the initial guess is. So do the same thing. You can get the other set of the relation, right? But look at those two equations. G1 plugging x0, y0 is just a number, and we just explain a little bit. If you have those two numbers, plugging here in and using the Fourier coefficient obtained from the very beginning, you can immediately just get a number. So the first one just a number, and I can also use. I can also calculate the G1 derivative with respect to x and y in Fourier space, right? Just you have one extra, maybe like ikx, if I'm taking a derivative with respect to x, or one extra iky coming out of here. But that's easy to calculate. But again, if I just plug in a number, a coordinate x0 and y0, and that's also a number. And x0 and y0 is the initial guess, which are also two numbers. So the structure of those two equations are linear equations with two variables, right? Because they are linear in terms of the unknown x star and y star. So two equations, two unknown variable. It's a linear equation. You know how to solve that, right? Linear algebra, immediately get an answer. So once you do that, you start with x0 and y0, and you got a value for x star and y star. And you can use the x star and y star again as your initial guess. Now, because it's going to push the solution a little bit closer to the real solution, right? So that will be your initial guess. So it's like I can also follow the same scheme, the Taylor expansion, but everything is the same. You just repeatedly substitute what you are getting as your initial guess and do that again until very quickly you will find that the x star equal to x naught, so nothing changes anymore, which means those two things cancel out, and higher order term, they are not important because they are exactly on top of each other. So that's the exact solution. Okay. So that's the way I used to get the atomic position. And now you have all these GPU that you can use, so you can parallelly let the computer to calculate the local maxima really quickly, maybe thousands. So you will get very quickly for every time frame what's the atomic position. If you are doing for example, dislocation dynamics, you want to see how the atom around dislocation move changes, and you can also quickly get that information from using this method to get the position of the atoms. All right. So as I mentioned, it's very straightforward, and since you have already been using the Fourier transform, so all this calculation should be easy for you, right? Okay. So that completes the final method I would like to introduce. Just use the Newton reference method to get the accurately the atomic position. Good? Question? Yeah. Okay. So that concludes my tutorial today. All right. Okay. Have you guys tried out the rotated crystal successfully to see that? You set a proper boundary. Do you see that the crystal is rotated and it's being confined in a stress-free box? I mean, yeah, try that and let me know if there's any difficulty of getting that, all right?
If you are trying to locate and find out the element n, they are supposed to be integers.
Right. Right.
For example, if I want to rotate around 20 degrees,
it's going to be very, I mean, M and Ij could be really, really large, right? For example, like 20 degrees, then you have to say whether how big M and M has to go in order to exactly give you tangent 20 degrees.
Most of the times I may not get to the integral.
Yeah.
So I have to go for some plus or minus 20 degrees. It's not always possible to choose the integer.
Oh,
the rotation of our choice because constraint.
Yeah. Oh, you mean for large angle, right? Yeah, large angle. Yeah, I think so. I mean, for example.
For example, any angle. For example, you have 10.89.
Mm-hmm.
Supposed to be 10.
Mm-hmm.
Then the end will go.
Oh, well. So okay. Let me understand your question correctly. You're saying that if we want to get something large, a high angle, no? Okay.
Integer angle.
Integer angle. But why do you need, so some arbitrary number of angle, is what you're saying, like 20 degree,
yes.
20 even, okay. If you want to do that, first question is whether there is a combination of M and N will give you so that, right?
Yeah, restrict, I mean, I'm not trying to find out, so we are restricted by this choice.
Yeah, so which means, well, you can get something very close to 20 degree, let's say. That's possible. So in that case, maybe M can go like, as like 2, 3, 4, all sorts of combination. Because as you can see here, if I fix M always equal to 1, M here is as small as 5, it's only 10 degrees. So there's not many choices I can have, like 4, 3, 2. And they might not have the proper correspondence of Ij. But what I can do is in between, right? I can have like M, for example, M equal to 3 and N equal to 15 and I and J equal to 6 and 9. That would be exactly the same system. But if I choose M equal to 3, then N could be 14, 13, etc. I have more choices, so I can refine angle by getting a much larger M and N combination, but which means you're going to have a huge size. But theoretically, you should be able to get any arbitrary angle. Yeah, theoretically. Wow. Is it because in MD, it's usually you're dealing with the cubic system, so orientation relatively you can just determine by that cubic vector, so it's easy to select the size of the system.
Even in MD, you want to get non-cubic orientation. Like for example, sometimes we have to deal with 1, 1, 1 aligned with that axis.
Right. Okay.
Then you need to choose 2 directions in the 1, 1, 1 plane,
right,
which are perpendicular to each other.
It's similar like this.
So that it can fit.
Right. So similar. Yeah.
One thing that we don't do, if you technically, I mean, we don't do, others do, is to get a random angle between two plates. Most of the times, our simulations we do single crystal or with a definite twin boundary.
I see.
Generic high angle grain boundary or generic low angle grain boundary, if you want to get, then you may have to do the same thing. Otherwise, you will not fit it in.
Right. Or it's going to be stressed. There's a very nice work by Matisse Plop. I think Marathon is his student. Yeah. So I think it might be a good idea for me to start sharing the slides, right? So you guys can check it out at Google Drive.
There is a drive.
Yeah. PowerPoint file is okay, right? PowerPoint.
Yeah.
Okay.
I'll just upload it in the drive. So
I see.
they have the link to the drive, so they'll be able to download.
So maybe I will send you the link for the lecture 2, lecture 4, and 3. Because lecture 1 is a lot of movie, like 100 megabytes. That doesn't make any sense, right?
But if you want a stick, I can give you and transfer.
I think we will do that in the end, but just for the technical content, like this equation, if you have the file, it'll be easier.
So when we are doing some mathematical assumptions, sometimes we are cancelling based on the boundary conditions, like theoretic boundary conditions. Twice we did that.
We are using, so the question is what? Again, sorry.
No, so do we need to always use the theoretic condition, or can we go for
I mean, depends, right? Like for solidification, you don't really need, periodic boundary condition will simplify the calculation because you can Fourier transform everything easily. For epitaxial growth, you will need a substrate, but you can also do that like periodic, up, and down. So I think it depends on the problem. I mean, for me, if I can solve that in Fourier space, I would prefer to keep the system periodic. Yeah, right. So.
But it is I can use the other boundary conditions also.
Yeah, you can use like no flux boundary condition, things like that. No problem.
So in the last previous lecture, we are cancelling with the mathematical terms based on the theoretic boundary conditions.
Oh, okay.
So
okay.
So that
Right. Well, one way you can use the periodic boundary condition to cancel out the boundary term, but that divergence always. I think there's a term containing like a derivative or psi itself. So if a boundary condition is saying there's no gradient, right? So that also satisfies. There's nothing on the boundary. So. Yeah, so most of the boundary condition, if you are not using periodic boundary condition, should at least satisfy the constraint that boundary term, the integration should vanish, right?